Hello everyone, I hope you all are doing great. We heartily welcome you all to our YouTube channel CAD CA Master. If you enjoy what you see, hit the subscribe button and turn on the notifications so you never miss an upload. Well, in the previous session we had covered the complete info about how exactly the finite element method works. So we went deep into the derivatives, the Taylor equations, and then differential equations, how to derive them. So what are shape functions, how exactly it is linked, and how at the backend algorithm will work to solve our problems. So that's all about the mathematical in-depth details. Now we'll see how exactly it is going to help us with respect to FEA and CAE domains. Well, so this is the agenda here. So we'll start with the engineering problems, how exactly we're gonna solve them. So we'll see the different types of numerical methods, and then we'll jump into the types of CAE domains, and then we'll just have a look into the FEA. So why exactly we need the FEA domains, so types of FEA analysis, the linear and nonlinear dynamic analysis, and finally the areas where exactly we're gonna use the finite element analysis. Well, let's get into this and have a look in all these topics. Well, so let me just activate the pointer. Yep. Well, so if we have the day-to-day engineering problems, how exactly we're gonna tackle them? So in the current industries, we utilize these three methods. The first one is the analytical method, and then the numerical method, and the experimental method. So we already know about the experimental method. So for example, the crash tests. So let's say if we have the lakhs of cars, so we're gonna utilize one or couple of cars and do the crash test. Even though if we do the numerical analysis, the CA tool, by using it, we do it. Even though we do test at least couple of cars with respect to crash. Yeah. So this is how we do experimental tests. And then for durability, then fatigue analysis. So we have some the tool rooms where we test them and then provide the feedbacks, and accordingly the components will be again like redesigned if it is failing or if it is performing well. So we'll proceed with the series developments. So yeah, this happens here. And then analytical method. So this is just to analyze and just predict it. Yeah. Now let's deep dive into the main focus of the session is the numerical methods. So these are the different types here. The first one is the finite element method, and then we have the boundary element method, finite volume method, and we have the finite difference method. Let's see one by one. The first one is the finite element methods. So what it exactly does is, so let's say if we have a numerical method, it will convert that continuum into a discrete domain which is composed of nodes and elements. So yeah, we know about the nodes and elements. If you are fresher or if you're new to the CA, I'm going to explain it later on. So what are nodes, what are the elements, what are the shape functions, how they are going to help us to tackle the numerical problems. Well, so all the calculations are made at the nodes, and the results will be in the form of the stress, displacement, and the strains. Okay, and then these nodes, whatever the results you're going to get it, so they will be interpolated to the elements. So it's a like average solution on this elements. Let's say if you would like to get to know about the stress results on a particular elements. Let's say if I consider a rectangle, and if you consider this area white area, I'm going to divide this into the different elements. Or if this is the area, we'll be having 4 nodes here, one here, one here, one here, and one here. So now if you would like to get to know the stress results, we can't have it on the nodes. So We'll average that with respect to here, the one minus stress. You're gonna get it on this complete element. So I'll see the elemental stress. Yeah. Likewise, we're gonna get the results interpolated on the elements. Well, so this is how the example. So you can see this is the model. So meshed it. So we have the at the back end we have the boundary condition that is fixed, and we can apply the load here on the top. This is going to deform, and you could see this is the one versus stress. So it is on the elemental, not on the nodes. So if you want to extract the nodal stress, that is also possible. Yeah. Well, now we have the boundary element method. So what exactly it does is, so it will try to convert the numerical methods into a discrete domain composed of nodes and elements. Similarly, so calculations, whatever we have it, that will be done on the boundary nodes, and the results are interpolated for the elements. So it is for the boundary nodes, not all the nodes. Okay. So for example, we have the heat transfer problems, right? So here, let's say if you consider this scenario, so if you're going to do the thermal analysis, so all the boundary node will be considered into account, and then the results will be related to the elements. We have the finite volume method. So the main thing is the Navier-Stokes equation for this. So if someone is from the aeronautical department, so someone knows aerodynamics, they will know this equation, how difficult it is, and to derive it. Yeah. So this particular method will be mainly used into the CFD problems. Okay. So this one, let's say if you consider this one, so we'll be having two types of flow simulations. One is the internal flow analysis and the external flow analysis. So this is a kind of domain we're going to build outside, and then we do the external flow analysis on this, so that we can just capture the aerodynamics behavior and the drag and lift force. Yeah, this is what we do on the external flow analysis. Yeah, internal, we just go ahead with the uh, the room analysis, ventilations. Yeah, the refrigerators, these all will come into the internal. Yeah. Well, finally we have the finite difference method, so which is called as also the Taylor-based series. Yeah. So I had already explained what is this Taylor series, how it is going to be utilized. It's very important. So this is discretization of the partial differential equation. So we already know what exactly the partial differential equations are here. So it is mostly used in advanced level analysis. So you could see first one is to deal with the computational fluid dynamics, yeah, and then electromagnetics and the engineering, where we deal with the nonlinear and dynamic time dependent analysis. We use the finite difference method, very important. So everyone mostly know about this terminologies and try to link everything with this, but very importantly, finite difference method also plays a very important role. Hope this is clear. Let's jump into the next slide. Yep, so very important. So domains in CAE. So what exactly says it's a computer-aided engineering. Okay, it refers to the computer software to simulate and analyze the behavior of the engineering systems. Okay, and then we have the different types of C analysis, which includes the most famous popular word, that is FEA, finite element analysis. Okay, so this technique is used to model and analyze the behavior of the structures under various loading conditions. Okay, so which involves dividing the structures into the small elements, and then it solves for the displacement, and you'll get the results in the form of displacement, factor of safety, and the strain. Okay, and then we have the computational fluid dynamics, CFD. Okay, so it deal with the behavior of the fluids, gases, and their interactions. Yeah, so it deal with the mainly the Navier equations, Navier-Stokes equations. Yeah, the fluid dynamics, and then we have it here. So it predicts the flow patterns and the pressure, temperature, and relevant parameters. Next one is the multi-body dynamics. So which is also a popular domain, we can say. So where we just deal with the mechanical behavior of the components. And then so this particular MBD involves in solving the equations of motion, so which will help us to predict the forces between the bodies and the motion between the bodies. Okay, so let's say the piston analysis and some of the vibrations, these all will come under this particular MBD. The thermal analysis, so which involves to deal with the thermal loadings, yeah, such as heating and cooling. Okay, so which helps us to solve the heat transfer equations and to predict the temperature distributions as well as the heat flux. Very important things. The next one is the electromagnetic analysis. So currently it is used in many industries. So to deal with the EVs and also such as the motors, transformers and antennas. Yeah, it is completely dependent on the electromagnetic systems and the components. So the equation used here is to deal with the electromagnetic effects are Maxwell's equation to predict the electromagnetic field, currents and the voltages. Yeah, one of the booming domain we can say in the CA right now. I hope you got to know about these all the domains. Well, so one more we have it. The current trending in the market is the optimization. So currently in the market we have the components, all the car manufacturers, the BIW trims, forging, sheet metal components, and also nowadays the cost of the cars and all very high. So each and every the competitors like let's say the Hyundai and Mercedes, you can take this Audi, BMW, and the Japanese cars and Chinese cars, Maruti Suzuki, Tata Motors. So all are competing, and very important is to save the cost, right? And save the complete sustainable design we should make it, right? So for that, to design a lightweight component is very important. So here the optimization plays very important role. So what exactly it does is, so it deals with the design of the engineering systems and the components, and we try to optimize them by just considering the various design parameters and the loading conditions, the different loads. We can even consider in the advanced softwares like the OptiStruct. We can able to include all the loading conditions like the crash and VH requirements and the SAME as well. So and then considering these all the loadings, so we take the objectives and define the constraints, and then we extract the load paths depending upon the optimization, and then try to re-realize the model by using uh, the retopology activators, and then finally we're gonna get the model. So yeah, this optimization is dependent on two things. One is the parametric optimization as well. One more is the non-parametric optimization, which where we extract the load paths and all these all things are there. So it's a vast domain. So there's a lot of things to explore in this. Yep. So these are the CA domains. I hope you got a brief idea about what exactly there in the CA world. Let's jump into our main terminology, FEA. So everyone has the question what exactly this FEA is. So it's very simple that it's just a type where we solve the engineering problems using this method. So by just considering the behavior of the structures and the component and the different loading conditions. Yeah, in short, so we solve the numerical equations like the partial differential equations and all. Yeah, so this is what exactly we do here. Well, so under this we have the finite element methods, and this we had already seen. So if you would like to know more about this, please refer my previous video so that you can get to know about each and everything what exactly under there in this FEA inside FEM. Yeah. Well, so in this FEA we have the different types again. So for the first one is the static analysis. Yeah. So the most famous analysis is the static analysis, where each and every the fresh graduate needs to learn about it and explore it so that he can get into the FEA domain. Well, what exactly we do here? So we know the equilibrium equation, right? So we try to solve it for the structures depending upon the various boundary conditions and the loading conditions, and predict, as I said, the deformation, strain, as well as stress. Well, if you consider a model, for example, so you could see this is the mount. So we have the different loading condition depending upon that, and we do have the boundary conditions. And then with respect to these neighbor component loading on this particular component, you could see the stress, hotspots, and you can even extract the factor of safety, and then the displacement, how it is behaving, and depending upon that you can predict what needs to be done. This is all about the static analysis, yeah. And the next one we have the dynamic analysis, where it is mostly dependent on the time varying loading conditions. So here the loading condition is the steady state. We don't this it's not dependent on the time. Here it is dependent on the time, the loading conditions. Okay. So for example, we have the impact analysis, the vibrations, right? So these all are mostly depend upon the time. So for example, we do have the natural frequency analysis, Modal analysis, damping, right? The random vibration and all, it will be considered into the dynamic analysis. So for example, if you consider this one, so here we can just see the nonlinear analysis, but in the form of dynamic analysis. If we would like to cross verify, we can even cross verify the natural frequencies of this component and the modal analysis of this, so that we can predict how it is behaving, and then yeah, proceed further. Next one is the mode analysis, so where we extract the eigenvalues and then we just predict the natural frequencies and the mode shapes of the components. It's very important in the current automotives also. So here we extract the mode shapes. Depending upon the mode shape, we'll deal what needs to be done, right? And then one of the major advantage of this modal analysis is to check the free components. Let's say if we have the whole automotive model, let's say a car, okay, and the vehicle. So there are so many connections, right? And the contacts you're gonna use, nuts and bolts, washers, these all things, adhesives, everything you use, right? RBTs, RBU2, RB3s and all. So you thousands of components will be connected. So if you do the modal analysis with respect to mode shape, if the component is flying, then you will get to know whether entire assembly is perfectly modeled properly or not. So this is the main reason we use the modal analysis to deal with the complete trims. Yeah, I could see if you have the BIW here, we have adhesives, RB2, RB3s connected to this complete BIW portion. And now this mode, there are so many modes, okay, very important. So in an automotive domain, so we deal with the torsion and the bendings, okay, the 6th and 7th, first 6 will be 0, as you all know, and then the 7th would be, it should be torsion, front torsion and the back torsion, and then the bending will happen, the front bending, rear bending, so even the middle bending, so depending. So after 6th mode, so these all the behavior will be expected, so very important. Yeah, the next one is the buckling analysis, so everyone knows it. This is also important analysis where we predict the critical loading factor, buckling factor, we call it 1.1 or less than 1 or less than greater than 1. Depending upon that, we predict whether the component is failing or whatever the loading we have used, whether it is under the limit or it is making component to fail. That we're going to predict here. Could see if you consider simple beam structures, so depending upon the loading conditions, how it is going to impact, that we're going to predict. Yeah, the next one is the fatigue analysis, where we deal with the repeated loading over the time, right? So that loading might be a cyclic or it might be variable, depends, okay? And depending upon this loading conditions, we're gonna extract the results in the form of stress or strains, and then we just add this into the fatigue analysis advanced tools like FE Safe and different tools, and then depending upon the material and the inputs we give in the FESAP tool, we're going to have the fatigue strength and the endurance limit of that particular component. You could able to see if this is the in mount. This is the region where it is going to fail, and then we'll check the strength here and then try to optimize it or redesign it or change the design so that we can have the better component which should last longer, right? Then we have the heat transfer analysis. In short, we're going to just deal with the temperature distribution and the heat flux in the structure, and then this particular analysis involves in the heat transfer equations to predict the temperature distribution. Yeah, well, you could see this is a simple chip. If you're going to define the inputs, the boundary conditions, and you're gonna get the results in the form of the temperature distribution and the heat flux, and then you're gonna predict what next to be done. So it is again transient, and the static also is there, dependent on time, how it is going to impact or how it is going to perform, that we're gonna predict. The final one is the non-linear analysis, where we evaluate the structures with respect to the large deformation, and even the non-linear material properties we're going to consider for this non-linear analysis. Yeah, so where we predict the plastic deformation and the material failure. So the crash test we can consider, right? And then there are various analysis we can do it. This is also one of this. So where we are trying to crush this particular structure. This is the rigid, and we have applied the load, and we have utilized the nonlinear material properties and the nonlinear response, and depending upon that, this is how it is behaving. Yeah. Next, again inside the dynamic analysis only, if you consider the dynamic analysis, we have the again linear and non-linear dynamic analysis. The first one is the modal analysis, where we try to extract the natural frequencies, modes of vibrations, and this is completely linear if you do just a natural frequency analysis. Okay, and then the dynamic responses will be extracted depending upon the modal responses and the superpositions. The response spectrum analysis, where we just extract the range of ground motion. Okay, and then we define this particular response spectrum, and depending upon that we try to deal with the particular structure and try to increase the performance of it. Yeah, so we'll be having the graph, and then from there, from that data, we'll see whether it is failing or not and whether it is under limit, and then we'll try to deal with that component. Time history analysis, so where we just again take the time history into account and try to extract again the graph, the spectrum we can call it. So here, in short, the seismic data we consider, and then we try to extract the results, and then yeah, it proceeds. Then we have the harmonic analysis, where we just deal with the sinusoidal kind of loading conditions. Yeah, so this is equable to see the harmonic load and the wave loading we consider in this case. And then we have the random vibration, so, and thus the wind turbulence, the ocean waves, and the random vibrations, like if you consider if the bumps, sudden bumps while you are driving, so these all are considered into the random vibrations. Okay, SCME load cases and all, we can use random vibrations and all and predict the results. Yeah, so that's about the dynamic analysis, and then we'll see these are the chart. In short, we can summarize it here. So analysis, in the linear we have the linear static analysis, and we do have the linear dynamic analysis as we have seen it here. And then in the non-linear we have the implicit non-linear analysis and the explicit non-linear analysis. Here the dynamic is different, non-linear is different, and linear is different. Terminology is important. Don't just confuse yourself with the dynamic and the non-linear. Okay. Well, so in the implicit non-linear analysis, what exactly we consider is the long events in few seconds, the small deformation, the gradual deformation we consider from every milliseconds. Okay, so for the simple material models and the model with less contacts, we use this particular implicit analysis. So we'll see where exactly it is used, and I have the example I'll show you. So in this cases, we're going to consider the material nonlinearity, geometric nonlinearity, and the contact nonlinearity. So there is a lot of things to be learned later on. I'll explain everything. Just remember these terminologies now. And then next, we have the explicit analysis, where it is going to deal with the components which has short events. Under the short events, we're gonna have the large deformations, so that will be considered and the results will be extracted. So here it's again the complex contacts will be there, large number of contacts we can utilize. It is again the wide industry. Okay, so we do the crash, drop test analysis, explosion, and so on. Yeah. Now, just to know about these implicit and explicit analysis in detail or in short, I have this chart here. So if you consider the static analysis, so structural problems, this force doesn't vary with time. Okay, I, loading is independent of time here. Yeah, and then we have the implicit analysis. We call it as quasi-static in middle. You can see we have the forming, we have the die and the blank. We gradually, slowly punch this sheet metal component. You could see the black one, and then it will try to deform and it will try to adapt to the die. Yeah, so this kind of analysis, if you would like to conduct, we consider that under categories, that is implicit analysis, that is called as quasi-static. Yeah, and then next we have the explicit analysis, which is completely impact analysis. In the short timing, in the short duration, this will be done, and then we'll get the impact of it on the behavior of it with respect to nonlinear contacts, material, and geometry. Yeah. Yep. And you could see this is in short to summarize. Okay. So the quasi-static used to represent the term slow dynamic process. Okay. Now, if you're considering the fully dynamic analysis, the time impact to the loading condition you're going to consider, that is constant throughout the time. Fraction of, if you're going to consider only 1 millisecond, yeah, and then the load will be constant throughout. But if you consider the quasi-static, with respect to time, it slowly increases, and at a certain time the load will be constant. So this is how the quasi-static implicit analysis will work. But in the dynamic, zook, one short load, and in fraction of seconds you're gonna get the deform model. Yeah, and then yeah, and this is very expensive analysis. You need to remember that. Yep, so now we have the different areas where we utilize the CAE tools to deal with the FE analysis. One is the sheet metal industries, where we do the metal forming and the packaging industries, and then we deal with this also. Yeah, the static analysis, forces and loads, and the fluid flow, that is the dynamic analysis, that is we consider transit as well as static, the aerodynamic analysis, okay, CFD. And then the molding, you know, the plastic injection molds, and even the castings, right? The molten metal will be flowed, and then this kind of analysis we use it, where we utilize mold flow tool for the plastics and all, and for that, yeah, it proceed. Moldex also we use it, and then the layouts to investigate them. So optimize the cycle time, and we have the safety. We have the different fields, the transportation, that is automotives, the commercial vehicles also we can consider. Yeah, the crash and the failure. Yep, and the acoustics to prevent noise. So these are the different industries. So now let's just deep dive into the one of the major industry, that is automotive. So in the automotives we have the different the domains, the BIW, trim, chassis, forging, sheet metals, and the plastics. So in this we have the a number of components, and then for that we need the FEA analysis to predict the behavior, performance, and reliability of the components. Yeah. So in short, if you consider the car parts, you could see a lot of components will be there, where we need to do the analysis and predict the component life cycle, as well as the strengths, and whether it is fit to work or it is sustainable or not. That all we need to predict. Now we have the exhaust system, we have the rims, we have the complete the under chassis, and then we have the side doors. Yeah, we have the BIW intercount. Yeah, so these are all the components, and we might have the knuckles here, we have the connecting rod. Yeah, a lot of components. We have the plastics. So these all the components will be considered for the analysis. Now if you consider the complete BIW, you could see these are the different the BIW parts. We combine them to create a final body in white model. So where we initially start with the engine compartment, and then we have the front floor, yeah, the rear floor we take it. So assemble these two, and then we go ahead with the side, left hand side, and the right hand side body sides, and then we have the rooftops and the upper back, and then this all will be assembled to the main body, and then we have the upper cowl, and then the low cowl, and then we have the trunk lid. These are all the outer BIW parts, to which will help us to cover the complete the main body, the hood, fender, the front door, and the rear door. Okay, so this is how it will be assembled in the normal the chain production. Okay, will be how the automation there. So it will start from this, and all the robots will try to assemble them in the chain. So it will take 3 to 4 days to produce a single car with all the process, by just combining them, adding the adhesives, connecting them, and then assembling all the required components. Yeah, it's all automatic robotics, and even manual interpretation is needed. So it's a complete, if you consider plant, each and everything will be implemented in series. So the car, like a single car will be produced within a couple of days, or 4 days, or 1 day, depending upon the speed or the requirement in the market. Yeah. Well, I think that's all about this session. So here we are at the summary stage. We had gone through the engineering problems, we had seen the numerical methods, different types of numerical methods, types of CAE domains, FEA, why we need it, the type of FEA analysis, linear and non-linear analysis, dynamic analysis, and areas where we use the FEA analysis. I hope you got a clear idea about what exactly these terminologies are, and where exactly we use the FEA and the basics of FEA. Well, so if you would like to become a CAE engineer, please do contact us. If you need any support, training, or guidance, we are here to help you out. So we can utilize our mail ID and the contact number. Yeah. So we'll continue in the next session.
We heartily thank you all for watching this video. If you enjoyed this video,
Don't forget to hit the subscribe button and give it a thumbs up. Follow us on Facebook, LinkedIn, and Instagram for behind the scenes content and the updates. Stay curious, stay awesome, and see you again in the next video.